Hello and welcome to another episode of Slam TV. I'm Professor Roger Yang, and today we're going to learn about confidence intervals for the proportion. Luckily for you folks at home, we've got a very special guest for you. 120% of the people surveyed say he's totally awesome. He washes his hands before and after using the restroom. He's Professor J.
Roger,
Cho.
it's an emergency. It's an emergency.
What kind of emergency?
Restroom 911, gotta go.
Gotta go? But Cho, we gotta do a show.
Ooh, wow, feels much better.
Glad you could join us.
Hey, Roger.
Hey.
Some nuts?
You know I'm nuts about nuts, but did you wash your hands after using the restroom?
Of course I did. Doesn't everyone?
I wish there was a statistical technique we could use to determine the proportion of students who actually wash their hands after using the restroom.
Indeed there is.
Oh, there is? First, why don't we remind our viewers of what proportion means?
Population proportion. Portion or percent of a population with some characteristic.
Oh, you mean like how 10% of the population is left-handed?
And only 1% of the population is truly ambidextrous.
I got you. You can eat with your left hand and your right hand. I wonder how we're going to estimate the population proportion of students who actually wash their hands after using the restroom.
We could construct a population proportion confidence interval.
Well, that is the topic of this episode. Maybe we should need to go out and collect some data?
Sure, let's creep and lurk outside some bathrooms.
Okay.
Wow.
Oof.
Collecting this data is exhausting.
Man, thank God we have statistical techniques to help us estimate the population proportion, because sampling everyone would be a freaking nightmare.
I know, it's impossible.
Well, let's take a look at the results. There were 120 people who used the restroom, so our sample size n is equal to 120. 65 of them washed their hands. And since we're interested in the proportion of people who wash their hands, in this case, washing your hands would be considered a success. So the number of successes x is equal to 65.
Ew! That means the rest, 120 minus 65, which is 55 people, didn't wash their hands? Gross!
That's disgusting.
Ugh.
How are we going to construct the confidence interval for proportion?
Well, first, we need to find the point estimate.
What's the best point estimate for population proportion, Jay?
Well, the best point estimate for population proportion will be sample proportion.
Oh, can you remind our viewers of what the notation for sample proportion is and how to calculate it?
Sample proportion is denoted by p hat, which is equal to x over n, where x is the number of successes and n is the sample size. We can find the sample proportion by dividing number of successes by the sample size. In this case, the sample proportion p hat is equal to x over n, which is number of successes, over sample size, which is equal to 65 over 120, which is 0.542 or 54.2%. That means 54.2% of the sample wash their hands.
Oh, that must be our point estimate.
Exactly.
And is that right in the middle of our interval?
It goes right in the middle. Then we need to calculate the margin of error for the proportion.
Oh, is that the same formula we use to estimate the population mean?
Oh, estimating population mean formula? No, that's so last episode. The formula for proportion is slightly different, even though it's similar. Let's take a look at it.
Oh, I see z alpha over 2 in the formula again. Does that mean we have a normal distribution?
Oh, speaking of normal distribution, maybe we should call norm again.
Great idea.
Calling boring norm.
Gentlemen.
Oh,
Hi, Norm.
We need help with figuring out the margin of error formula for population proportion.
We saw z alpha over 2 in the formula, and we thought that this might be your area of expertise.
Tis.
Wait, why are we using normal distribution? Isn't it binomial distribution? Because either people wash their hands or not wash their hands. So clearly this is binomial distribution situation.
Did someone say our names? Do you need us? We're kind of busy right now.
No worries, binomes. I got this. we're going to use the normal distribution to approximate the binomial distribution.
Why would we want to do that?
Because we want to use the central limit theorem again. Plus, binomes are pretty busy right now.
Wait, does that mean we don't need binomes ever again? Binomes are replaceable?
Yeah, can we always use the normal distribution to approximate the binomial distribution?
Well, actually, we needed the number of successes, NP, to be at least 5, and the number of failures, NQ, to be at least 5.
Wait, I know P is the probability of success, but how about Q?
Oh, Q is the probability of failure. It's just 1 minus P. For example, if P is 0.25, then Q would be 1 minus 0.25, which is 0.75.
Okay, so you're saying if NP are bigger than or equal to 5 and NQ are bigger than or equal to 5, then you can use normal to approximate binomial? I don't know if I'm convinced.
Let's look at a couple of graphs to convince you. As you can see, this binomial distribution looks really blocky and not that normal. But this binomial distribution looks a lot more normal.
Oh, I see that. So in our washing hands example, we had at least 5 people who washed their hands. That means we have at least 5 successes. And 5 people who didn't wash their hands, which means we had 5 failures.
That's right, Roger. Fortunately, we did have enough successes and failures in our grueling data collection excursion. So we can use the normal distribution to approximate the binomial distribution. Now, if you'll excuse me, I need to use the restroom. Gotta go. Bye.
Man, now
wrong?
I gotta use the restroom.
What? This is like in the middle of the show.
As opposed to at the beginning of the episode when you had to go?
Rude.
Anyways, I don't feel comfortable using a public restroom unless I knew at least 50% of the population washed their hands.
Oh wow. Well, first we need to find the margin of error. Then we can construct a confidence interval. Then we can figure it out.
Man, how long is that going to take? Let's get to it. Why don't we look at the margin of error formula? I understand the critical value piece, z alpha over 2, but what's that crazy looking thing to the right?
Well, I know. That's just the standard error for proportion. We are using central limit theorem where we're treating sample proportion as sample means.
Oh, okay, cool. Why don't we plug in the numbers and calculate the margin of error, E? In our case, we have a sample size n equal to 120. P hat, our point estimate for the population proportion, was 65 over 120, which is equal to 0.542. Q hat, which is 1 minus P hat, which is 1 minus 0.542, is equal to 0.458. Our critical value z alpha over 2 is equal to 1.96. Plugging all these numbers into our formula, we get E is equal to 0.089.
Do you remember what we do with the margin of error E?
Yeah, we add and subtract the margin of error E to our point estimate in order to get the endpoints of our interval.
Exactly. So 0.542 plus 0.089 is equal to 0.631.
That's the right endpoint of our interval, right?
And the left point of the interval is 0.542 minus 0.089, which is 0.453.
Oh, so our interval is 0.453 and 0.631. Does this mean over 50% of the people washed their hands, Jay?
We are 95% confident that true proportion is within the interval.
Maybe we should explain to our viewers what 95% confident means.
Oh, it's just a statement about process of making a confidence interval.
What does that statement say?
If we repeat this process a lot, 95% of the confidence intervals will contain the true proportion.
And 5% won't?
Exactly. Let's say we collect data every day for a month or for even a year.
What? I'm not going to stand in front of a bathroom for hours again, not even for a single day, never mind a month or a year. This definitely crosses the creepy line.
And each of those creepy days, most likely we'll get a slightly different sample, which will give us slightly different confidence interval. Most of them, 95% of them, will contain the population proportion, and some of them, 5% of them, will not contain the population proportion.
So is this interval we found one of the ones that actually contains the population proportion?
We don't know.
What?
All we know is that 95% of those confidence interval contains a population proportion. In inferential stats, we can't really say anything with 100% certainty.
Is that always true?
Yes.
Oh well. Maybe we can help the viewers interpret this confidence interval.
Sure. You say you wanted to know proportion was more than 50%, right?
Yeah.
Let's look at some different cases. If the interval was entirely above 0.5, like this picture, then we have evidence that the population proportion is above 0.5. If the interval was entirely below 0.5, like this picture, then we have evidence that population proportion is below 0.5.
What if the endpoints straddle the interval, like in our confidence interval? What if 0.5 is within our interval?
Then this interval does not provide evidence that proportion is above 0.5 because the interval contains values below 0.5 as well. For example, the interval contains 0.48. What do you think that means?
That means the true population proportion P could be 0.48. That's 48%. That's definitely less than 50%. Ew.
Exactly. Our confidence interval suggests that proportion could be more than 0.453. That could mean it could be 0.457, 458, all less than 50%.
Man, I don't think I like this result. I'm definitely not using a public restroom. Let me make sure I understand you right. If our interval was, I don't know, for example, 0.531 to 0.731, then can we definitely say that our proportion P is above 0.5?
Not really, Roger. Not definitely. It only suggests that we have evidence that proportion is bigger than 0.5. Remember, in inferential stat, you can never say anything definitively.
I can definitively say that not washing our hands after using the restroom is disgusting.
You got that right, Roger. Disgusting.